All right, hey guys, welcome back. So I want to sort of pick up from where I left off yesterday. Quick note, again, I made my announcement yesterday afternoon, hopefully you guys saw. I made a correction to yesterday's lecture. I sort of messed up a conditional probability problem, which was a little embarrassing on my end. But I think I made the correction now. So check out that PDF I posted yesterday if you haven't already. I fixed the example. Basically, it was better to solve it with a tree diagram. So I did that in the example there. And then I included an additional example that I made up to sort of do conditional probability with the formula that I reminded you of, you guys of yesterday. So check that out if you haven't yet. And my bad for making that mistake. I'll try to not let that happen again. I know that can be frustrating on your guys' end. It's frustrating on my end too, so it happens, but I try not to let it happen. Anyway, and if you ever notice me doing anything weird on the board that seems like I'm wrong or something, just feel free to chime in. I like to be corrected. I don't take it personally. So if you ever think I'm making a mistake, just let me know. Okay, so I just, like I said, I want to pick up from where I left off yesterday. So yesterday, I introduced Markov chains. So just to remind you, just briefly, what this means. A Markov chain was a stochastic process. So that means we're just doing some experiment or whatever in stages. I have like these sub-experiments. Everything's broken into stages or steps. It's a multi-stage process. It's a stochastic process, and a Markov chain is a special kind of one. It's where the probability and we'll call this Pij, of transitioning. It's falling off. Transitioning from state I to state J depends only on I and J. So maybe said slightly different way, this probability does not depend on what happened in previous steps or stages. So the probability of transitioning from one state to another doesn't depend on what's happened in the previous stages of this experiment. It just matters of where you are now and what you're looking to go to next. That's it. So I gave you an example of something that was decidedly not Markov, and that was this ball example where I had a bag full of different colored balls, and we were removing balls without replacement. And we're doing it without replacement. So when I pull a ball out, I don't put it back in the bag. I set it aside. That was not Markov because after I've taken out so many balls, the probability of which color am I going to get next not only depends on what color ball I just drew, it also depends on what color balls I drew before that, because I'm doing this without replacement, so I'm not putting the balls back. So it depends on how many balls I've pulled, and it also depends on which colors those balls were. So it depends all the way back to the first stage, not just on whatever stage you're currently at. And so that is not a Markov situation. But I also gave you guys a couple examples of things that were Markov chains. One of them was flipping a coin a bunch of times. That was kind of a too simple of an example to really be interesting. But flipping a coin a bunch of times qualified, because the probability was just always a half for each stage. And then I ended on a different example about the weather. And I want to sort of pick up at that one just for a second, because I'm going to introduce a new piece of technology for us to use to study these things. And I figure we might as well start with an example that we already have in place. So if you guys remember this weather example from yesterday, this was looking at, there were two states. There were two states possible here. It's either going to be rainy or sunny. And maybe I should write these in a different order. Maybe I should say sunny or rainy, just to be consistent with yesterday. Sunny or rainy. These are the two possible states that I allowed in this weather example. And I gave you different probabilities for transitioning, say, from sunny to rainy or getting sunny 2 days in a row and so forth. And so if you remember, the last thing I did yesterday was draw the transition diagram. So I introduced transition diagrams yesterday. And this is like a diagrammatic way of representing a Markov chain. And so in this example, it was like this. So refresh our memories. I have two circles. I have sunny and I have rainy. And then I draw arrows from one to the other, and I label them with the probabilities of transitioning from one to the other. So if we remember from yesterday, the probability of going from a sunny day to a rainy day was 1/4. The same numbers from yesterday. So this should be 1/4. The probability of transitioning from a rainy day to a sunny day was 1/3. The probability of going from sunny to sunny again was 3/4. And the probability of going from rainy to rainy again was 2/3. So I drew this transition diagram on the board yesterday. Okay. And so this allows us just to visualize how this Markov chain works. These are the different transitions possible. Going along the arrows represents transition, and then the numbers just represent the probability of making that transition. So that was one thing I noted about the Markov chains yesterday, was we're always talking about transitions. I'm talking about going from one state to another. And so when I ask questions like to solve problems in these, you're always going to have some starting point. I'm going to ask, like, if it was a sunny day today, what is the probability that it's rainy 2 days from now, or something like that? We always have to start somewhere. And yesterday we started with a sunny day, for example. So we need somewhere to start because we're always talking about transitioning. Sunny days don't come. Okay, anyway, I don't want to harp that point anymore. Let's just say we have to have a starting point, and we talk about probabilities of transitions from one state to another. I think yesterday I emphasized the fact that these were conditional probabilities. It's really saying the same thing. This 1/4 represents the probability of the next day being rainy, given that today it was sunny. The conditional thing. Okay, so this is great having a transition diagram. It's a nice visual way to represent a Markov chain and to see what's happening in our system. I can use it to do computations. I did it yesterday. You basically, if I want to ask what's the probability that it's sunny, if it's sunny today, what's the probability that it's rainy 2 days from now? All I have to do is start at sunny, and then I have to find all the possible paths that start from sunny and end at rainy after 2 steps, because I'm asking for 2 days from now. So like I could go from sunny to rainy. That's 2 steps. Sunny, rainy. Or I could do sunny, rain, rain. I think those are the only 2 possibilities, right? But I could take those 2 paths, and as I go along a path, I just multiply the numbers that I hit. So if I go sunny then rainy, that's 3/4 times 1/4. If I go sunny to rainy, that's 1/4 times 2/3. And then I just add up those numbers that I get. And so we did that problem yesterday in class to illustrate that this can be used to actually solve some of these problems and calculate probabilities. What gets a little more tedious, though, is like, what if I wanted to know whether or not it's going to be rainy 10 days from now? What are all the possible paths through this, starting from sunny and ending on rainy after 10 steps? I don't know. There's a lot of them. There's a lot of possibilities now because I have 10 steps to work with. So I could do like sunny, 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 rainy, rainy, sunny, rainy. I could trace out all kinds of crazy paths that are 10 steps long. And so it gets a little harder to work with. It's a little more cumbersome to answer that kind of question with this. And so it would be nice to have instead of like a picture that we draw, a nice mathematical object to encode all of this information into. That would be really helpful. And it turns out we do have such a thing, and it has this, well, it shouldn't really be a surprise that it's going to be a matrix. It's going to be a matrix. So I warned you guys yesterday that this topic combines probability matrices, and this is our first hint of matrices, the transition matrix. So this transition matrix is just the matrix whose entries are these Pij's. So again, Pij is the probability of going from state I to state J. So these are just our transitional probabilities, these conditional probabilities. Okay, they're going to be these numbers here. So I'm basically going to just take these numbers and put them into a matrix. And I'm just going to do it in a specific way so that it is sort of, we're making a consistent choice of where to put the numbers. So let me show you this example here. I want to convert this into a matrix. Here's how it's going to go. I'm going to draw my matrix over here. And the idea is this. I have two states. So maybe sunny is state 1 and rainy is state 2. I've written them in this order. So I have my first row is the sunny row. The second row is the rainy row. The first column is the sunny column, and the second column is the rainy column. Now to fill in the numbers, all I'm going to ask is, in this first entry here, this should be the probability that I go from sunny to sunny, i.e. that should be this arrow here. This is 3/4, because this goes from sunny back to sunny. So 3/4 should go here in our matrix. Now over here, I'm asking what's the probability of going from sunny to rainy. So I find the arrow from sunny to rainy. That is labeled with 1/4. So this is 1/4. Okay, so now in the second row, I look for from rainy to sunny. That's this arrow here, rainy to sunny. That's 1/3. And finally, from rainy to rainy goes here, and that's this arrow here from rainy back to rainy. That's 2/3. So this matrix, 3/4, 1/4, 1/3, 2/3, is our transition matrix for this Markov chain, representing this weather situation. This is our transition matrix. Okay. So for now, in this section, 8.1, we're just interested in describing these Markov examples. And we can compute some simple probabilities by chasing out paths and stuff on transition diagrams or tree diagrams. As far as the matrix goes, I want you guys to get comfortable finding these, but we're not going to use the matrix yet to problem solve until 8.2. So later on this week, I'll show you exactly how to use this to solve problems. Basically, it's going to boil down to matrix multiplication, but I'll hammer out the details later on. For now, we just want to get comfortable finding these, and I'll give you guys the promise that this really will be useful for solving problems. Okay. The last thing I want to point out about the transition matrices right now is the following fact. So look at that transition matrix. And there's something I want you guys to notice about it, which is this. So notice the numbers in each row. The numbers in each row add up to 1. So, for example, 3/4 plus 1/4 is 1. 1/3 plus 2/3 is 1. The numbers in each row add up to 1. Okay, that's going to be kind of important later on. And so I wanted to just point this out now that this is always true of a transition matrix. A transition matrix always has this property. The numbers in each row add up to 1. So if you're being asked to find a transition matrix and you write one down, and you notice that one of your rows doesn't add up to 1, then you've made a mistake and you need to go back and check your work. So on one hand, this is like a sanity check for you guys to check your work. On the other hand, it's going to be important later when I talk about probability vectors. So I mentioned vectors before when we defined matrix multiplication. We had row vectors and column vectors. We're going to have some special kinds of vectors called probability vectors later on, where all the elements add up to 1. So I could rewrite this and say our rows are probability vectors, but I'll hold off on that and just tell you for now. The rows add up to 1. That's an important property of transition matrices, so we just want to note that this is always true. Okay, because somehow they're representing probabilities. I mean, if you think about it, if I already know that I'm starting sunny, then the only possibilities are that the next day it's sunny or the next day it's rainy. Those are the only two possibilities I'm allowing. Since those are the only two possibilities